I've been spending a lot of time recently back in the past restoring a pair of SX62A Hallicrafters radios, and I'd like to move back to the present. Don't have a DeLorean, so I'll just have to do it as best I can. But anyway, back to the present and picking up on an experiment that I promised weeks ago using the analog discovery and a MiniCircuits attenuator, Pin Diode attenuator. I'm going to make a couple of changes to the experiment. Instead of using a TFAS1, I'm going to be using a TFAS1. This is made by MiniCircuits as well. Let me show you the difference. The TFAS1 is a 1 megahertz to 200 megahertz switch based on pin diodes. It uses this circuit in which a signal is put into one end of this. It's relatively symmetrical, and extracted from the other end is basically two transformers. But the interstage part of the transformers, in other words the secondary of the input and the primary of the output, have a diode ring of pin diodes so that you can apply a voltage, and as you apply the voltage to those pin diodes, they turn on or turn off. And that's the reason why that it's called an attenuator or a switch. Switch because if you put enough current into the input, this essentially becomes a direct connection from the input to the output, and you get the same thing on the output that you have on the input with the normal trivial losses that any circuit has. On the other hand, if you remove the current, in other words, you put no current through these diodes, there's a very high attenuation between these two. So, okay, why didn't I use a TFAS1? Well, the reason is actually the price. It's $60 for this, and that's not an extremely high amount to pay, but most of what you're paying for is the box that it comes in and the BNC connectors. Basically, you pay about $10 for each BNC connector and about $10 more for the large machined box. Now you can buy essentially the same circuit that's in the TFAS1 in a different form factor. This is a attenuator switch that is in a package suitable for through-hole, in other words, printed circuit board mounting. Now they also make them with surface mount. I find this particular form factor to be the most useful. These only cost about $20, therefore you can buy more of them. First thing we're going to do is we're going to show you how this circuit attenuates an RF signal, or basically provides you with a variable attenuator. But before we do that, let's talk just a little bit about a pin diode and what it is. A pin diode, unlike a regular diode, is not a junction between a P material and an N material. Instead, in between is an intrinsic layer. And depending on how thick this layer is, this layer will store charge. And essentially what happens is this. If you've worked with diodes before as switches, you know that when you forward bias a diode, signals will pass through it. When you remove the forward bias, there is a certain amount of stored charge in a PN diode, and that charge has to leave or be swept out of the junction before the diode will really turn off. That is called the recovery time. If you insert an intrinsic material in here, that recovery time becomes much longer. More charge is stored in the intrinsic material. So basically, you might ask, why in the world would you make the diode slower? Well, the answer is, if you make the intrinsic material the right thickness, the charge stored in the intrinsic material will remain there for a long enough time that you can get through an entire cycle of an RF wave. Now, at some frequency, the RF wave will be stretched out so much that the diode will be turned off for too long and all the charge will disappear, at which time it stops being a pin diode essentially, and it just starts being a regular turned off diode. But as long as you keep the frequency high enough that during the off time of the RF, the intrinsic material remains charged, or some charge remains, the diode stays turned on. Now let's see what we're going to be doing with the analog discovery and how we're going to perform this experiment. On the screen is the display, the Waveforms display for the analog discovery. Waveforms is the software for the analog discovery. And at the top, I have a 2 megahertz, 1 volt signal, that is 1 volt peak, or 2 volts peak to peak. On channel 2, I have a 10 kilohertz, 200 millivolt signal. And we'll show you how we use these in just a minute. This is going to be the carrier. Eventually, we're going to use this and the attenuator switch to produce AM modulation. But right now, this one is turned off. Here on the bench is the experiment itself, set up in a proto board. Here is the attenuator switch, the MiniCircuits. Of course, this is the analog discovery, and right now we are using Waveform 1 and Waveform 2 and ground. Those are the only signals coming from the analog discovery. Now, I point out that the analog discovery has oscilloscope capabilities, and we could use that instead. I am instead, for this experiment, going to be using a Rigol oscilloscope, partly because the display shows up a little better on camera than sometimes the oscilloscope does on the analog discovery. As I've pointed out before, if you are looking at your computer screen, it looks perfectly fine, but sometimes it doesn't reproduce well on a camera. So what do we have here? Well, the input, waveform number 1, is a 2 megahertz, 2 volt peak-to-peak signal. That is shown up here on the Rigol on the top screen. This is the 2 megahertz. Channel 2 is the output, and as you see right now, there's no output. I'm using a 5 volt supply that you see right down there to provide current to the input of the attenuator. So what I'm going to be doing is turning that voltage up to 5 volts. And as I do, watch the oscilloscope and you'll see channel 2, that's 0 volts, that's 3/10 of a volt, 1 volt, and eventually 5 volts. And as you see, the scales on these are the same. As you see, the peak-to-peak voltage on channel 1 is 1.99 something, basically 2 volts. And the peak-to-peak on channel 2 is also 2 volts. So in other words, at this point, the attenuator is out of the circuit. Everything is passing through. And that's with 5 volts applied. Now, what I'm going to do is reduce this to about a volt. And then I'm going to turn on the second channel of the analog discovery there. And what I'm going to now do is slow down the scope to show you what is happening. In essence, we have produced AM using the attenuator. In other words, what is happening is we are driving the control signal from almost cut off to fully on. And now what I'm going to do is I'm going to reduce the bias voltage down to about 0.5, or in other words, a half a milliamp. And I'm going to increase the amplitude of the input waveform. Now you see what is happening is, as the waveform arises and turns on the pin diodes, more and more of the RF is allowed through. However, at this point, there is too much signal, and basically it's turning off the pin diodes for a large segment of the modulating signal's waveform, which in this case is 10 kilohertz. Now I have adjusted the bias and the input signal to produce what is essentially 100% AM modulation. 100% means that the signal reaches a peak. At the peak of the modulating signal, the RF signal is at its maximum. At the minimum of the modulating signal, the RF signal is close to or right at 0, and the envelope follows the modulating signal, which in this case is 10 kilohertz. What we've been trying to demonstrate here, how the MiniCircuits ZAS3 or TFAS1 can be used to illustrate modulation in a lab. Once again, using the analog discovery to provide the test signals. And we could set this up, though I'm not going to do it for this experiment, just to keep it a little shorter. We could set this up so that the analog discovery is also used as the display instrument. In other words, replacing the Rigol oscilloscope. So I hope this has been of some help, particularly if you have had some confusion over pin diodes and attenuators, and maybe their use as switches or as modulators. Once again, this is part of a series of experiments that I have been doing in evaluating how the analog discovery can be used in a modern RF communications lab. In this particular case, using a MiniCircuits attenuator. Hope you enjoyed this, and I hope you'll stay tuned for some future experiments along the same lines.